In this video, we look at the code that will be helpful, necessary to be able to complete assignment number 2. Remember, you can always go back to the series of videos getting started with RStudio and R, and you can also look at the video on code related to assignment 1. Some of that, some of what's covered there might be useful for trying to understand something that you can't do here. So first of all, at the top, like usual, I've commented, created in my script. At the top of my script, I've got some comments, code to help in doing URBS 362 assignment number 2. It's by me. I'm going to remove all objects just to make sure that our environment is empty. So I highlight the code and then command return, as I did in the video for assignment number 1. I'm also going to change my working directory so that it makes the paths that we use to access the files a little bit shorter and easier to understand. Next thing that I do is I read in the data. We'll call this CDS. So it's commuting data sample. I'm going to highlight this and enter. And actually, I'm going to add this too. I'm going to say reading in data. Should have done that before. Okay, good. So now we have a sample of the data that we used. In the video on doing assignment 1, I used commuting data. It was longer. It had 200 and almost 300 observations. Here I've taken a sample of 20 observations from that one. So this is a sample compared to the population. And our data set is called travel data sample. Now we're going to go through the code necessary to do the calculations that are necessary for the assignment. To start with, we'll calculate the arithmetic mean of distance, because we need to do a series of different things here. Basically what we're going to do in the assignment is we want to calculate the confidence interval for the mean, the population mean, and afterwards we'll do some linear regression. In order to be able to calculate the confidence interval, we need to have a series of different pieces of information first. So the first one is the number of observations in our sample. This is relatively straightforward, and we've calculated this before and on assignment 1. So rows of CDS, that's the number of our observations. And then we're going to calculate the mean. So we take the sum of the distance variable, and then we're going to calculate what's distance bar, the mean of distance, the sample mean, which is sum dist divided by the total number of observations. Now we have dist bar. So this is our estimate of the mean and our estimate of the population mean. Now we're going to get the sample variance. In order to do this, I create 2 new variables, just like I did in the code for assignment 1. So the first is just a variable which is the difference between the distance and the average distance. And then I'm going to take the square of that. So the square of the difference between distance and average distance. Finally, or not finally, the next thing I want to do is take the sum of that. So remember that to calculate the variance, it's kind of like the average of the sum of the squared differences. And that's what we've got here. The variable is going to be called sum dist minus dist bar squared. So that's that whole term, the sum dist minus dist bar squared. It's the sum of that. So we have sum and then this variable dist bar squared. Finally, we calculate the sample mean by taking the sum of dist bar squared and dividing that by the number of observations minus 1. Remember, this is a sample, so it's not the total number of observations, it's the number of observations minus 1. Next thing we need to calculate our confidence intervals is we need the proper critical t value. And so we can get that proper critical t value, which I've called here critical t, by using the qt function. And here what we've done is we've got 1 minus alpha divided by 2. So since the alpha that we're interested in is 0.05, because it's a 95% confidence interval, we put in 0.9, or sorry, 0.975, And the number, because it's a t distribution, it's necessary to have the degrees of freedom, and the degrees of freedom is the number of observations minus 1. So we can calculate that critical t. This calculation, the critical z, if there's a question on the assignment that asks you about critical z relative to critical t, and this is how you would calculate that critical z. Finally, we're going to go to actually calculate the 95% confidence interval. And this is based on the equation 7.7 in the New Bold textbook. So the first thing that we're going to try to calculate there is, one of the things that we need is for our equation is we need the S of distance, so that is the sample variance, the square root of the sample variance, the sample standard deviation. So we take that, we've already calculated the sample squared, the S squared, so the variance of distance. So that's what we calculated above. And now we're going to have the margins of error. So basically our confidence interval will be our estimate of the mean plus or minus our margin of error. And so the margin of error here, ME, will be the critical t that we got from R here before, times the standard deviation of distance divided by the square root of n, which is the number of observations. So now we can calculate our margin of error, highlight, Control Enter, and then we can calculate the upper and lower limits of our estimate. Lower limit is dist bar, our original estimate for the mean, minus the margin of error. And then the upper limit is our estimate of the mean plus the margin of error. So that's relatively straightforward. Last thing we'll have to do is to create, or the second last thing that we'll have to do, but the last part that's related to the confidence intervals and the margin of errors is a hypothesis test. And so in this circumstance, this is different than on your assignment, but what I'm going to do here is assume that we have a hypothesis. Our null hypothesis is that mu is equal to 10,000 meters. And notice if we look at dist bar is 11,475, so this is less than the estimate that we had. And that H1 is that the mu, the true population parameter of average distance, will be greater than 10,000. So in order to do that, we calculate our t. Here's our t value, and we're saying that we're using the formula, which is dist bar, so the average distance that we calculated minus the hypothesis of 10,000. We divide that by the standard deviation of distance divided by the square root of n. So if we highlight that, Command Enter, there we go. Now we have our t. Our t statistic here is 0.42, and I'll leave it to you to try to interpret what that means, 0.42. Actually, that's not true. I've written here in the code, since the critical t is 2.093, the t that we estimated is less than our critical t, and we don't reject this hypothesis. So there, I gave you the answer, at least for this data sample that we've used. Finally, the last thing that we'll do on the assignment is to estimate a linear regression. So linear regression is pretty easy. I'm creating an object here, LM1. That's where all the information about the estimate is going to, or from the estimated model is going to appear, the coefficients and all that. So we're calling it LM1, and I'm assigning to that the linear model. The linear model takes as arguments the dependent variable, and then after the tilde, this little squiggle here, it's called the tilde, we have our independent variables. So we've got age, or explanatory variables. We've got age, male, and FT worker, and these all come from the data set that's CDS, so data equals CDS. So now if we highlight and then Command Enter here, we'll see there's no errors. We see that it's blue and that it's gone through. You'll also see that there's a big, in our environment variables, we've got this thing called LM1, which is a list of 12, and it basically contains all kinds of information. If we want to see the information in a way that we typically summarize information for regression models, we can use this function, summary of the object LM1. And here we see we've got most of the information that we want about our regression model. So this is the call, that is the model we've asked it to estimate. So distance being explained by age, male, FT worker. Gives us information on residuals, which we don't talk about. We have the coefficients. So each of these coefficients, these are the estimates of the coefficients. So this would imply, for example, if we look at age, that for every additional year of age, people will travel 189 meters less. The other coefficients can be interpreted in a similar way. And, actually a little bit differently, because male and FT worker are both binary variables, so it's not interpreted in exactly the same way. The way we say it here for male is we say that males will travel, on average, 7,708 meters more than those who are not male. And in this case, there's only one other classification, so those are females. We'll also notice that we have our standard errors and our t-values, and importantly, our p-values. We'll notice that all of these p-values are much larger than 0.05, so none of these variables are actually statistically significant, and this is probably because the size of the sample is so small. It remains for you to see to what extent these results are similar to those with the data set that you're using on the assignment.